Hello everyone. It's our pleasure to have Alexis here to share about his work to us, and this is an amazing work, and I think it's really the state of the arts of quantum computers, where he will show us what is the how the phase transition in random circuit simplics look like. Alexis, the floor is yours. Thanks.
Okay. So thanks for the introduction and thanks for the invitation. I'm very happy to present our work. Just a few words. So I'm an experimentalist, so I'm mostly gonna concentrate on the experimental part. Um, if you have any question at some point, if I go too fast on some aspect, please stop and ask question. I will be more than happy to answer them. Of course, I should say this has been a work collaborating with a lot of people. I was not alone in this work. I couldn't have done it alone. And here are a few of the main people, but there is also like the full Google Quantum AI team behind that work. Okay, so the big picture is we want quantum computer to be able to go beyond classical computer, right? And the next question is, where can quantum computer offer such an advantage over classical computer? And the answer is not that clear at the moment. There is few problem where quantum computer can bring advantage. The main one that everybody cares and would like to see is decision problem, something like the Shor algorithm, where there is a yes or no answer to a question, like, can I factorize this number? This will be extremely helpful to have, and a clear demonstration of beyond classical computation capability. This, with current devices, is not yet possible or achievable. Like, our devices are too noisy to allow this. So there is other category of problem where we could still find a beyond classical advantage. One which is also very important for physics and chemistry is computing expectation value. So for instance, you have an Hamiltonian and you want to compute some quantity related to it. This is very important problem of physics and chemistry, for instance, local polarization on some quantum model or the energy level in chemistry to predict like chemical reaction. This, again, there has never been shown yet a practical quantum advantage of using a quantum computer over a classical computer on this problem, because they are hard just to reach because of the noise on device. So if we go down the ladder of problem we can do, there is still one problem that we can do where quantum computer can outperform classical one, and this type of problem is sampling problem. The idea is that with a quantum computer, we can very easily sample a bit string from a desired quantum distribution, and the idea is that sampling, like doing the same classically, will be extremely hard, exponentially hard. And this is where random circuit sampling belong. It's to this category. It's like a minimum example of something where quantum computer are very good at, but like classical computer will struggle as we go to larger and larger number of qubits. And the idea is that this is still true if we have like a noisy device. So my first section will be about random circuit sampling. I will try to quickly explain what it is and maybe present our newest result. So since we are working with superconducting circuits, we are bound to a 2D geometry. Here you have like a small sycamore chip. So it's like a square lattice where you can play entanglement gate, so I-swap-like gate. So this is the unitary of the matrix between on each edge of this 2D graph. We choose to use the I-swap-like, which look like this. It's not a textbook I-swap, and we choose to not do a textbook I-swap because with this gate, we have the maximum fidelity. So like we are the least sensible to noise. And then we construct a circuit which is just an alternating of single qubit gate on every qubit and 2 qubit gate. And we just repeat this according to a pattern to span the full chip. The pattern is important, as we will see next. And the single qubit gate are taken randomly from a set of gate given here. And we are making sure that we are choosing non-Clifford gate as well as Clifford gate, because if the full circuit is Clifford, this could be efficiently computed by a classical computer, and we do not want that. So what the output, what the distribution that we are trying to sample from is, it's called Porter-Thomas. So here I'm giving an example. So this is like a 12 qubit, this is just a 12 qubit circuit that I just run on a simulator, and I try to compute like all the probability of each bit string. And as you can say, it's a very hairy, like you have a forest of peaks, which just depend on the peak. So there is no clear structure, and this is normal because we are looking at random circuits. If you were to get like a uniform distribution, like so, or a fully noisy distribution, you will get this dashed line here at 1 divided by your size of your Hilbert space. This distribution, even though it's like hard to predict all of the bit string distribution, has a property that it's a Porter-Thomas distribution. So now, if you look at the probability of finding a bit string with a probability p, so this is like just taking the histogram of this probability, you will see an exponential decay as the amplitude increase, as the probability increase. So for random circuit, even though a single instance probability map like this is really hard to predict, the distribution is generically known, and it should be like a Porter-Thomas distribution. And this is what is hard classically to sample from. No, experimentally, we don't get exactly this. So this, since we are on 12 qubit, it's still very easy to do like just to try to get like all of the all of the probability for each bit string. So this is what we do. We just do a lot of sample, and we get the orange distribution. And as you can see, there is quite a large discrepancy between the two. So since we only have access to a noisy device, we have to construct a benchmark first. We have to construct a benchmark to tell us, is like the sampling that we are doing even correct in the first place? So to do that, there is this technique called cross-entropy benchmarking. So the idea of cross-entropy benchmarking is that you have two distributions and you want to compare them. To do that, here in the regime where it's classically computable, you just take your random circuit and you compute the ideal output distribution, which is this forest of peak. And then you just sample, you do a few samples on your hardware, and you compute this cross-entropy benchmarking quantity, which is taking the probability of the bit stream you just sampled, right, with some pre-coefficient depending on n's number of qubit minus 1. And then you average over all the bit strings that you sample on your hardware. So this is really nice because experimentally, we don't need to get the full map of all the bit string, right? We just need to sample from the hardware, and then we can compute this quantity even if we don't have, we didn't probe, like we don't have like the probability distribution over the full Hilbert space, which can be extremely hard even experimentally to get. So in conclusion, what's cross-entropy benchmarking is that it allows us to measure the fidelity of a state after a random circuit when the distribution is close to Porter-Thomas. And this is actually an important thing, is that you have to be close to a Porter-Thomas distribution for cross-entropy to work. We will see this a bit more later. So now what we can do is that we can use cross-entropy benchmarking on small system to benchmark the fidelity of our device. Here is an example on a 16 qubit, 16 square qubits, where I'm plotting the cross-entropy benchmarking value, average over 20 circuits and a few shots, as I increase the depth of my circuit. And as you see, as I increase the depth of my circuit, I'm getting more noise and the fidelity decay. This decay is exponential. And this gives me a very good estimation. By fitting this exponential decay, I got a very good estimation of the cycle, like of the error per cycle in my circuit. Just as a note, this cross-entropy benchmarking is what we use to benchmark 2-qubit gate. So we do exactly this technique on 2-qubit gate, and we can estimate the fidelity of our 2-qubit gate using this technique. And practically, with cross-entropy benchmarking, usually we are able to benchmark the fidelity of relatively large device, and we can go up to like 30 qubits. But then after that, it's become practically unreliable because you need to compute like all the probability for all the bit string in the Hilbert space. So it's become less practical after this number of qubits.
Sorry, I have a question
Yes.
over here. So like after 30 qubits, then what kind of like benchmarking do you guys use? Just kind of be curious on that.
What
Because
do
you
you
say
mean?
no, as in like now you can use cross-entropy benchmarking to basically characterize the errors up to 30 qubits, right? How about like larger than 30 qubits, and what kind of like metric that you guys use to characterize it?
So if you start to get like a very scrambled state, like a very generic state with more than 30 qubits, it starts to be very hard to actually measure the fidelity. Like cross-entropy benchmarking is extremely nice because, you know, if you have like an Hilbert space of 30 qubits, this is 2 to the power 30 probability. Like it's a vector of 2 to the 30 that you need to compute. But the magic of it is that you don't need to get them experimentally. You just need to sample a bit. So it's very efficient way of computing like the fidelity of the state. But as soon as you reach 30, computing all the probability is extremely expensive and you don't really do it. So what we do usually is that we cannot look, right? We have to look at, or we look at Clifford state, right? This you can still do and efficiently. So you just create Clifford state and you look at the fidelity, or you just do patches and you try to look at the fidelity of the patches and see if they actually make sense. But you cannot measure the fidelity of a generic state for more than, I don't know, like easily at least, for more than 40 qubit or 60 qubit.
Right.
Does that
Okay.
answer the question?
Yep. Yep. Thanks.
Like basically you need something that you know the outcome. Otherwise it's just very hard. And just also I should note that this look at the whole bit string. XCB look at the whole bit string. It doesn't look at local observable. So like, you know, a local observable you can be spoofed, or you can have like a local observable that look good enough, but the global state is not good. XCB doesn't like actually care about the full state that you have on your full device. So it's actually a very good characterization of your full device, not just on just of a single local observable where you can maybe be fooling yourself.
I see. Got it.
So this was this was basically what Google did in 2019, where they demonstrate the first so-called beyond classical experiment. So I will go a bit more in depth for this plot. So on the left is what is called easy circuit. Easy circuit here just means that we can compute the distribution probability and verify the circuit. So we can do benchmark on those circuits. Here, what happened is that the pattern here, so you have to look a bit closer to understand the difference between the two patterns. But this pattern, the EFGH, this pattern is actually easy for some method, I think it's tensor network method, to actually compute the state or the probability distribution at the end. So you can actually benchmark, and this is what's done on this full curve for the full circuit. So this is the full circuit in circle. Even though, like it, as I said, like the classical verification for the circuit require quite some time, like 5 hours. It starts to be non-practical. But then you can do other circuits, like the patch circuit, where you cut your chip in two, and you do two small patches that are relatively easy to simulate classically, right? Because they are just like 25 qubit now, and this you can do on your laptop. So you simulate each part, and then you take the fidelity as a product of the two, and you get this like the blue cross on the plot. And finally, there is this elided circuit. This is a slightly more complex circuit. I will not go too much into detail, but the idea was trying to find something that was trying to actually propagate to have like a Porter-Thomas distribution of the device without with still being classically tractable. And so with these three, what you can see is that all the points like fall right on top of each other, right? They are all on top of each other, which means that for those three circuits, the XCB, or the cross-entropy benchmarking, is actually measuring the fidelity of the state that you have been preparing. So since they all agree, like this gives us confidence into saying that, okay, the fidelity, if you are doing random circuits, the fidelity that you get at this depth for this number of qubits is roughly this much. Now, there is this second part on the right. And the idea here is that now we are taking a pattern, A, B, C, D, C, D, A, B, that is different and that is like specifically designed to be hard for classical computer, tensor network method and such. The idea now is really to make the pattern as hard as you can, so at some point classical computer cannot keep up. At the time of the writing of the paper, they did two sets of three sets of circuits: the full circuit, the elided circuit, and the patch, also in this regime. And for both patch and elided, they can actually verify that the sampling is actually what is expected, right? And this is why you have dot in this plot. But now for the full circuit, the complexity was so high at the time that they couldn't compute the probability. So they couldn't compute the cross-entropy benchmarking for those circuits. So what's important in this plot is not what is shown. What is shown is just to give you confidence. It's what is not shown. What is not shown is the bit string for the full circuits on those depths on this pattern. So like really, like what's happened is that there is a bunch of circuits that give you a bunch of bit string. And for those, the claim is that no one can verify them or like even mimic them, like try to construct like a sampling that will look like that. So this was a bit optimistic at the time because I think few years after, tensor network contraction have catched up, and now there is method to actually do similar tasks, but it's still required to go on, like, I think this experiment was, I forgot the name, but it was done on a very large I forgot the name, I'm sorry, on a very large, like cluster computer. So it's not an easy task to do that, but I think today, like I'm pretty sure today, those circuits have actually been verified by other groups because tensor network contraction have improved. I will give an estimate about those circuits. But the idea is really here, you try to get into a regime where just simulating your circuits to get the bit string distribution at the end is just too hard, but also sampling from this distribution become just incredibly hard for classical computer. But like for quantum computer, it's just easy. You just run the circuit and you look at the bit string at the end. So 3 years after, we redid the experiment on a larger device. So now, instead of 53 qubit, we did it on a 70 qubit. And this time we didn't do the elided. We just do a full device, 2 patches and 3 patches. So there is a slight discrepancy, but here you see in dot, those are experimental data that we have verified. And then the line is, the continuous line is the discrete error model, which is basically multiplying the process fidelity of each gate with measurement and idle error. And you see that there is a decent agreement between those two. Now, if you compare to the plot that I showed you before, this one, which was on 53 qubits, now the number of entanglement gates is like 60% more. And each one of those gates has better fidelity, which has actually allowed us to get to this depth for the same overall fidelity. I would like to, it doesn't look like much because the curve looks very similar, but everything is exponential in this experiment. Like the fidelity like kills the signal exponentially. So to get like the overall fidelity like for more qubits at large depths is actually quite I would say like we were really happy when we saw this result. And now what we did is that we did run a full circuit, so a circuit on the full device now, at one depth, and we just collected a very large number of shots for this circuit. And now the claim is that no one, for this specific circuit, no one will be able to verify it first. So this is going to be like the hardest task, verify this sample, but no one can actually take the same circuit and mimic the output distribution. So, and this is basically like, if you look at the hardness, which is basically the number of flop, and you put it in 2 log, this shows that with other experiments done by other group, there is kind of by year like an increase of hardness of this task with time. Is there any question on this part?
Yeah, I do have one trivial questions, like for the patches, right? How do you decide like where to cut? Just like by experimental kind of
We try
concentrations,
to,
or yeah.
yeah, so it's not easy actually. So you want to have very large chunk on each patch, and you want them to be how do you say, as bulky as possible. You don't want to do lines, for instance, because this line will kill the spreading of entanglement, right? And so you will have to get deeper to do Porter stomach. So you really want to get chunk as bulky as possible. So this is why we did 2, by the way. We did 2 so we can have like a, you know, like believe what we were seeing were true. We wanted to have like 2 different benchmark for what we get, so we can actually get confident into that the bit string that we have is extremely hard.
Right. Okay.
But like, let's say you see like so here we did 3 patches and 2 patches also, because 3 patches was actually, I could run it on my laptop, so it was very to quickly check. But 2 patches, those 2 patches require a bit more computational power, so they were done offline, and they took a few hours to run.
And then the patches must be kind of symmetry, right?
No, this doesn't matter that much. Since the fidelity at the end is just a product, you just want them to be bulky. That's it.
Right. Okay.
I think I see a raised hand.
Yeah, thanks. So I'm just wondering, I saw a paper a few years ago saying that when you have depolarizing noise, the cross-entropy benchmarking overestimates the fidelity. So
I think you will have to be slightly more explicit, because usually we are like in every model we are usually assuming almost like we are assuming 2 qubit gate depolarizing model, and this usually give us like XCB will give you exactly this depolarizing noise if you are in the Porter-Thomas regime. If you are at low depths, it's not true, but in the Porter-Thomas regime, you are almost going to get there.
okay, thanks.
Okay, so just to highlight improvement that has happened. So if I look at the single nodes, I look at the element error rate, which were into the solid line. Single qubit, we have improved them by 30%. The 2 qubit gate, we have, like, this seems like a small improvement, but it's actually a pretty like significant improvement on those 2 qubit gates. And actually, like, our biggest win for this experiment was really on the readout, where we divide almost by 2 the error rate. And with this, as I said, we were able to do 60% more gates, so like 60% more volume in the total circuit, which is it's a lot. And I think like currently there is no other experiments that is doing something as complex as this task for a quantum computer. So this we have map of all the fidelity. So these are the maps. It's not always homogeneous because the systems are not that easy to work with, but overall the fidelity is good everywhere. Now a bit of complexity estimate. So we actually worked on estimating the cost of running the simulation on Frontier, which is currently the largest high performance computer in the world, I believe. And those are the number of flops that we estimate for the 4 random circuit sampling experiments that have happened. And as you see, the first experiment from 2019, now we estimate that to have 1 million noisy sample, we will just need 6 seconds on frontier. So what this shows is that since the first release of the 2000 experiment, there has been like a very, very large improvement on tensor network contraction for those random circuits. Like there have really been like an incredible work done by several groups to actually tackle this problem. Because like at the time, nobody really tried to look into those random circuits and try to understand them with tensor network. But after the big claim that Google made, people started to really look deep into it. And nowadays, like there is this belief that those tensor network contraction are pretty much optimal, not yet fully there, but very close to it. So we are pretty confident in this number, even though, you know, if someone come up with a breakthrough, this number might come down. But this is what we use to do this plot here, and it's like the time, like the flop needed to compute one, like the amplitude probability of 1 bit string. If you look, so this is the scale of the time that will be taken into, like that it should take on frontier. And as you see, so there was 2 other experiments that are still a few days on frontier, but like this experiment is now in the 50 years range with what we think are the best method available for tensor network contraction. This actually in the supplement there is very like a detailed explanation of the tensor network contractions that was done for this work. Now, like just a few words on the hardness of this task. So this is for the tensor network contraction method, and so this show in color the hardness or the number of flop to realize the tensor network contraction for one amplitude. And as you see, there is first like there is at when you look at low number when you look at low depths, there is an exponential increase of complexity up to this dashed line, and then after the complexity kind of plateau at a fixed number of qubits. And so what this say is that, you know, like for the size of our device, which is 70 qubits, if we were to go deeper, they will not necessarily be more complex. It will be roughly the same complexity. So really, like now, the next generation of experiment for those type of experiment to really be even more hard for tensor network contraction will have to have more qubits and deeper. So really, like the frontier for those experiments is pushing like further and further. Okay, we also tried, I'm going very quickly on it. We also tried a popular method, which is like MPS computation. And what we showed is that we are already like those are like the number of, so this is like the lower bound for dimension showing like the memory needed to do the simulation. And from what we see, it's like completely impossible. Even from the previous experiment from 2019, it's impossible to use MPS to do those, at least not in the proposed method that we have seen, to do the simulation. Like tensor network is actually the best method available for the system. Okay. So now we will talk a bit more. So this is random circuit sampling and a bit on an overview of why people care, or like we care about doing this experiment and redoing it. It's because today it's the only proof that quantum computer can do something better than classical computer. And no, like I will try to know. I will look at 2 cases where you can fool this experiment. So if there is any question of RCS, no will be the time.
Yeah, for the audience, if you have any questions, then you can unmute yourself or type it in the chat. Then I could like have you ask the question if you want. So yeah, currently I didn't. Oh yeah, I do have one question for the Chris. Like I know you will be like out of your kind of like is on the basically kind of like computational side. Like do you like just now you mentioned that beyond like you have a threshold where like beyond that basically the hardness like doesn't increase that much, right? Do you have any intuitions of what would it be like normally
Yeah,
we will expect like deeper circuit will have like it's much harder to estimate, right? But over
yeah.
here give you
I
yeah.
my experimentalist interpretation, so take it with a grain of salt, is that at some point you reach the boundary of your device. So the entanglement grow, but at some point you reach like the full device. You have entangled your full device with itself, and starting from this point, it starts to be hard. Like okay, we are entangling in a very generic way. We are not doing like Clifford gates, but you have really like entangled your full device, and after you will not create more entanglement, or like the hardness that you are going to create are going to be minimal compared to like the initial burst of like just creating more and more entanglement. And this was kind of the idea, right? That MPS can capture this small entanglement part, or like the spreading of entanglement, but we are already way farther than where this method can actually apply. I think like the stopping of the growth is really due to entanglement just as spread to your full device.
Right. Yeah, I really like this kind of explanation because it made intuitive sense for me as a physicist. Yeah. So yeah, I kind of like agree with you. We have one question from Gordon. How does Monte Carlo sampling perform for this task?
So you will, I think you will have to define like what you call Monte Carlo sampling here. Um, I will say several people like because of the 2019 experiment, really like a lot of people have tried to actually show that this was easy task, but like the only method that actually managed to really give results was tensor network contraction. This has been like the only method that actually have like really is really like the competitor for those. Maybe there is other method unknown yet, but like tensor network is clearly like the winner in terms of classical method. I am not a specialist enough in Monte Carlo sampling to tell you how it perform like nominally, but I know that tensor network is the best we have right now.
Yep, I think he's
Okay.
fine with yep.
Okay, so now actually I will try to. So this is more like so. So this was just a repetition of what was done in 2019 with better hardware to show that we have really like we are trying to scale up the number of qubits. But after the first manuscript on this experiment on random circuit sampling, the community tried to the community started to question some assumption behind this experiment. And one of them that come often is at low depths, it's not clear what happened, and XCB doesn't seem to work properly. So when you didn't reach Porter Thomas, what happened? So this is like the anti-concentration point. So I remind you the definition of linear cross-entropy. It's look like this. So you are looking, you know the probability distribution from simulation, and now you are just summing over all the bit strings that you have sampled, and you sum it this way. If you look at depth equals 0, or like you have not applied any circuit, you start from 0 from a single bit string in this experiment. So this quantity, like the cross-entropy benchmarking, will be like the probability distribution will be picked right on one bit string, and your cross-entropy will be 2 to the power n minus 1. So it's very large, clearly not the fidelity of your state. Then as you start to just like increase the number of cycles, you are picked toward like large probability, but you start to be a slightly delocalized in probability. And this is shown here. And at some point, at the anti-concentration point, you are completely delocalized and you look like Porter Thomas with an exponential decay of the probability distribution. So what the message here is that if you are looking at too short of a depth, like the anti-concentration point is not reached yet, and the anti-concentration point, and basically like your XCB, your linear XCB is going to tell you a number that is way higher compared to what you should have with your fidelity. And so we actually indeed measure this experimentally. So this time we try to go to very low depths and try to see what happened. And as you can see, so this is for different size chain. You see that at low depths for both 1D and 2D, you have a behavior that is proportional to the Hilbert space size, right? You have 1 divided by for the Hilbert space. So it goes very high, and it's not a good benchmark of fidelity. But as you increase and go through the anti-concentration point, you start to have this exponential decay as a function of the number of cycles that indicate that now you start to be closer to the fidelity. And like one of the findings that we have is that there is like a finite crossing depending on size, indicative of a crossover or of a phase transition, but like a demarcation between two phases, one where you are not anti-concentrated and one where you are concentrated. So what we bring here is really like what noise does to this point. Okay, so this was just like at small distance, and it's now I would like to talk about what noise does to random circuit sampling experiments, and mostly not random circuit sampling, but mostly like on cross-entropy benchmarking. So after the 2019 experiments, there was a lot of work towards spoofing random circuit sampling. What spoofing means is that you just say, I can generate a sampling with classical hardware that will look as good as a noisy hardware, because the idea is that noise will kill correlation on your device. So surely you can take advantage of this and create something that will just give you a sample that look as good. And this is what spoofing is. It's just trying to make a method that perform as good as the quantum hardware. So why did you need the quantum hardware in the first place? So this is generally called as spoofing. And so one of the questions that we really wanted to answer was, can you try to roll out the spoofing algorithm? And also, like, when does a NISC algorithm and those type of experiments actually mobilize the full device, Hilbert space? So this is really what we wanted to tackle. And so now let me take like an example. It's a silly example, but it's an educative one. So I'm taking a 1D random circuit. I have a left and a right part, and I'm removing any gate between those two parts, right? So I have two distinct circuits playing in parallel on my device. And the fidelity per cycle on the left is fidelity left, and the fidelity on the right is fidelity right. Now, see, if I go deep enough, I will reach Porter-Thomas for both of those halves, but I will not reach Porter-Thomas for the full system. If I do a bit of algebra, the fidelity of the total system is the product of the fidelity time the depth at which I go. But the linear cross-entropy benchmarking with depolarizing noise look like the following. So you have the fidelity as the first term, but then you have the fidelity of the right and the fidelity of the left. So on this simple example, what it says is that if you run two circuits in parallel on your device, you cannot claim that the XCB on the full device will give you the fidelity on your full device. And this is actually what we already knew when we do like patch XCB on the big experiment, right? We never do the full XCB. We do the XCB on each patch, and then we multiply the two to actually get the fidelity. So for some, if your circuit is ill-designed, the XCB will not be a good benchmark of fidelity. Now, we are going to construct a model out of this intuition. So we are going to add it's weakling, not weakling, it's weakling. So we are going to add one gate every now and then with period t. By doing this, we allow correlation to spread between the two halves. And if we go deep enough, the full system will reach a Porter-Thomas distribution on its bit string. The fidelity is still given by the same, but now the linear XCB is given as a coefficient in front of the fidelity of the right and fidelity of the left, where lambda is the spread of correlation on the system. And you see there is like the dependence on the periodicity of the link. So now what you see can happen is that your XCB, even though you have reached like a Porter-Thomas distribution, it has several contributions. And one of the contribution is the ones that you care about. It's the fidelity of your device on your full system, but the other two are fidelity on the halves. And this, you don't really want to see them. Those will actually spoil. Usually, since lambda is smaller than 1, those two terms goes to 0 very quickly. But you can see that there is a regime in which it's not the case. So to see that, let me allow to do this experiment where I have my chain. So this is experiment of data. I have the chain, and on the right side, I increase the noise, but only on the left side, on the right side. So by doing so, what am I doing? I'm making like the fidelity on the right goes to 0. So in this XCB value, XCB formula, I'm gonna kill the first term and kill the second term, but only keep the last term in the expansion, right? And now, in the weak noise, I will have the XCB that is going to be linearly proportional to the fidelity or to the added error. But as soon as I reach the strong noise regime on the right side, I'm going to have the XCB that is just going to be proportional to the fidelity on the good side, the side where I didn't add the noise. So now what happened is that I have, in a setting, I have the linear cross-entropy benchmarking that is just giving me half of the system fidelity. And of course, this fidelity is higher than the full system fidelity. So what this means is that if I believe here the fidelity that I get, I'm getting a much higher fidelity benchmark than what I should, what the underlying fidelity is. So really, in this strong notch regime, XCB fail as a benchmark. And this is what spoofing is relying on, is that XCB can fail as benchmark of the fidelity. And here what's really striking is that this is due to noise. Noise is creating this situation. And so this is why we were talking about noise-induced phase transition. So we wanted to know like the situations that you will encounter experimentally is more of a homogeneous noise on your device. And so here what we did is that we did two chains, one with low noise, so still a weakling, one with low noise, and one with very strong noise. And we look at the predicted fidelity that we know, like the predicted fidelity that we have measured from each element, which that we know should predict roughly the fidelity. And we look at the fidelity of the full system. And as you can see, in the weak regime, the measured fidelity XCB on the full system goes very close to the predicted fidelity. But in the strong noise regime, there is like a gap between those two, meaning that basically in the strong noise, the fidelity that you get is way higher than what you actually were expecting. And this is completely agree with what we were saying before. And so even though it's more subtle in this case, in an homogeneous case, if you have too much noise, once again, you will not get a good benchmark with cross-entropy benchmarking. So we wanted to explore the phase diagram in one dimension. So the parameter order is not super easy to define, but what we tried was to use the predicted, so the cross-entropy benchmarking divided by the predicted fidelity. And so in the weak noise regime, this goes to 1, but in the strong noise, this goes to 0. And we have increased the periodicity, we have decreased the frequency of the weakling application to see what happened. And we have looked at the both measured fidelity and the predicted XCB fidelity. And what is interesting is that for all those systems, there is like a finite size crossing of this ratio of predicted divided by the measured fidelity that we have seen. And we interpret this crossing as a phase transition from a weak to a strong noise regime. And actually, analytically, we have a model that shows this phase transition. And so here you have like a summary of our experiment where we delimit a strong phase transition between a low noise or weak noise phase and a strong noise phase. And we have analytically and numerically tried to see what happened when you go closer and closer to a normal chain where you have one weakling apply every other cycle. Why didn't we do experiment here? So the issue is that this experiment, you need to get to measure like the cross-entropy benchmarking with very high precision, right? If you look at before, you see like we measure XCB up to 10 to the minus 4, 10 to the minus 5, and those experiments require like a large number of shots, like billion of shots, and it starts to be too much experimentally to be reasonable. So at some point we just say we are limiting to 10 to the minus 3, which is already accumulating shot to a lot of time, and we just, and so for just the normal chain, we couldn't observe the phase transition because it was too far away, and we don't have the resolution to see them. We have also explored a 2D system to be sure that this will apply to the main experiment in 2D. And indeed, we also observe phase transition with a crossing point, but in 2 dimensions, it's a bit more messy because now the points actually depend a lot on the pattern that we are using. But we still observe a transition. And so where do we stand for the experiments that I showed you before? So we have done like a lot of numerics. So those numerics are very expensive as well because you need to get like to very large precision. So we couldn't go to very large size. But what we see is that they all clearly define a region where there is like a strong noise behavior, where XCB is not a good benchmark of fidelity, and a weak noise regime. And we have chosen a very pessimistic boundary here, given by the gray and white difference. And the experiments that I show you on the left stand at the red star here. So we are actually, and this is a log scale, so we are actually pretty deep into the weak noise regime, which really like give us confidence that this experiment cannot be spoofed by just taking patches of the circuit and simulating them. Okay, so with this is the conclusion of this talk. I think what I've hoped to show you is that we have now performed like one of those very hard quantum experiments, actually the hardest we can do currently, and that we have improved our fidelity quite a lot to push the limit of what is possible in this regime. And finally, we have discovered these noise-induced phase transitions that actually limit a bit, like if you think of it, this actually limits the size of the device that you can use for such an experiment for a given noise. So if you want to get beyond, the complexities that we have done here, you need to increase both the size, the fidelity of your device by quite a lot in order to be sure that you are in the right regime and you are actually hard classically. And with this, I want to acknowledge like the full team. So now we are quite a lot of people in the team. And as I say, like the scope of our mission is now very large. And yeah, thank you for your attention. And if you have any question, please go ahead.
Yeah, thanks, Alexis, for the very, very interesting talk. And I'm very, very impressed on like how much you guys have like improved the device. Like this one metric is like 60%, like for 3 years, then this is like very, very impressive. And also it's kind of like cool to see how you guys like explore the effect of noise and see how it affects the like random sampling task, for example. So for the audience, if you have any questions, feel free to unmute yourself or type the questions in chat that I could ask. In the meantime, I think I could like ask a question as well. I saw in your papers, and you have already described in your slides, you mainly consider the depolarizer noise models, right? I'm just wondering, like, when will these type of assumptions break down?
So here it's we are doing random circuits, right? And we are all the curves that I show you are mostly average over random instances. And the idea behind that is because if you start to randomize an average of a random instance, you are actually effectively are having a local depolarizing noise. So it will break down but for us, like experimentally, we have found it to be pretty accurate for those random circuits. But now if you start to do like structure circuits, something that doesn't have this randomness, you will start to accumulate coherent error. And as soon as you have coherent errors that can accumulate, you are going to deviate from this model. This, I think, is especially when you go deep, structure will actually make your error more complicated.
Right. Okay. And the other question that I have is more generic actually. So just like you mentioned that you like couldn't like go to two. Okay, so you say that basically like if the shots is too many to measures, then it's basically infeasible, right? But as we increase the system size, basically the number of shots requires would be getting much larger. And like, do you think that at the point like we couldn't like go even larger because the number of shots is too much to measures for a given task?
So the size doesn't really impact the number of shots that you need. It's really the fidelity that impacts it. You need the number. I forgot the formula, but you will need something that is proportional to your fidelity, because this is the size of the signal that you are trying to measure, and then you have the shot noise on top of it. So roughly, like I think if we stay in the 10 to the -2, 10 to the -3 range, or even 10 to the -4 for one circuit, we will be able to measure it in a reasonable time. But like 10 to the -6 or 10 to the -5 on the uncertainty of what we measure, this is just start to be too much experimentally. Right. It is just unreasonable. It's probably possible, but it starts to be a huge pain for the experimentalists.
I see. Okay. So we do have one question from the audience. Maybe Kishore, you can unmute yourself and ask questions.
Yeah. Thanks for the nice talk. Like, I mean, it was really insightful. Maybe I missed part of the talk, so like, I'm sorry if you already covered it. So, so there was this paper like early last year on actually two papers I would like to mention. So there was one paper on polynomial time algorithm for noisy random circuit sampling by Umesh Bajirani and Dori Taharanov and others, and basically using the algorithms of Gao and Duan. I mean, basically the idea that when you have like a depolarizing noise of a strength gamma, what happens that only those polypaths contribute, which correspond to like low Hamming weight. So they gave this algorithm, and they basically managed to refute the X squat below the sublinear depth, and more. They gave a polynomial time algorithm for like simulating noisy random circuit sampling. So I mean, like after that's like the result, like I mean,
I can comment on this result actually. Yeah, so I will tell you, like, so first I would like to mention that if you look at the manuscript, the last sentence of their abstract is our algorithm is not practical in its current form and does not address finite size random circuit sampling based quantum supremacy experiments, right? So the first thing to say is that the algorithm right in the scaling, like when you start to look at infinite size, and also like I will say the limit that they are taking is not like as I said, as you increase size, you will have to increase fidelity. And this is very similar to what we are saying in this like result, that like there is a finite, like at a given noise rate, you have a finite size correlation at which you can go. After that, correlation die because of noise. And in their papers, they are taking, my understanding is that they are taking the limit of fixed noise and they increase size. And this, as I said, you will get a correlation length that after that you will die. But if you were to scale noise down as you scale size, this will not work. And experimentally, this is what you need to do, right? You need to diminish noise as you increase size. There is no hope. Noise really limits the size of the device you can make.
I see. So you are saying that all the asymptotic analysis, basically the moment you are assuming constant noise, like like per circuit component, will not work, because obviously, like for large in the asymptotic set, like it.
I'm not saying it's not working. They are good, like these are a good paper. But like what I'm saying is that
no, I'm not talking about, like, I'm not talking about the result, like implication of, I mean, about the result being good or bad. I'm talking about, the implication of the result on the hardness of simulating the circuit classically. And I'm saying that, like the moment you, like the way I'm understanding, you're saying the moment you have a constant noise per circuit component, the hardness that we have, which was guaranteed from cross, like, X quad conjecture, I mean, that does not hold. And that's why you will have a polytime algorithm for circuit simulation, noisy circuit simulation.
I believe yes.
I see. And something like I don't quite remember exactly, but I was reading the paper, and you guys haven't had a table, like where you also had this number of years of simulation or something. So for the previous experiment, I think it was like few seconds or something, like the experiment which was done in 2019. So like for that, like did you guys do some numerical classical simulation yourself, or is it based on some classical simulation that somebody else? Yeah, exactly.
Yeah. So I would say like this table are based on estimation. Like they are estimating like memory constraint and contraction. Like they are based on what is actually an improvement on the best method out there. So they are really, in this sense, they are quite optimistic time of running this, but they are really like what we believe is the bottom on estimate. But nobody, or maybe someone will do, but like it's too expensive to run those frontier to get to see if it's actually going to work.
I see.
But yes, those are estimates based on like constraint of using frontier. And I would say like frontier is like 1,000 times more powerful than the previous one, summit. So there is like a factor hit that was there as well.
That's beautiful. I see. So Alexis, like, if I like, look at so previously we had this estimate of 10,000 years, right? And like, I mean, in the original paper, like, I mean, which you guys published, like the Nature paper, like the quantum supremacy paper, and then people try to bring it down and down and down, and we at the moment we see like 6 seconds or something. And then there was this paper by Aronson and others, Aronson and Chen, and then Aronson and Gunn, who suggested that like maybe because based on cross entropy quantum threshold assumption, cross entropy heavy output generation task should be difficult. But the cross entropy quantum threshold assumption, the complexity theoretic assumption, which is obviously will make sense in the limit asymptotic set. All the complexity theory is asymptotic theory, right? I mean, it's not a finite size theory. So the hardness guarantees which was there coming from X quad is no longer present. We don't have any complexity theoretic
no, there is one thing. So there is like there is a result. So it's not yet fully proved, but like nobody has demonstrated like there is let me find back but we know that sampling like the hardness scale like bad. There has been no proof. Like there is one missing proof, I believe, but people are pretty confident because of numerics that it's hard. I forgot like exactly. I'm not a theorist, so
numerics people are constantly pushing the thing, right? I mean, once we have I mean, what I'm saying is the main guarantee which was due to Aronson and Chen does not hold, right? I mean, so I mean, at the moment I'm not aware of any other thing. So okay, coming back to something very like I mean, disjoint and all. I saw a similar paper also coming up a few weeks later, like after your paper from Maryland group. Like I think they also did some kind of I think Braden Ware, Alexis Gorshkov, and some people from Maryland. Basically, they studied this kind of phase transition in sampling task. Like, do you have any comment on that paper? Like, in which aspect?
Yeah, it's the same as what we observed.
It's same, huh? Okay.
Yeah. They posted a theory and simulation paper after the experimental we published on the archive. Yeah.
I see. I see.
But it's the same. Yeah, I believe it's. If it's a paper you are referring to, it's the same. Yeah.
I see. I see. Okay. Okay. Thanks a lot.
I think like, yeah, like I will say like they are doing a very nice simulation, and they can push the precision very deep because they are doing simulation. Experimentally, we cannot do that.
I see.
So I think the two work are complementary from this respect.
I see. Thanks for the comments. Like these were really clarifying. Yeah.
Yeah, you're welcome.
Cool. So actually, like I do know like some guys who have kind of questions on more on the computational side. So like, do you think like we can like ask the questions to you after the email, because we have like running out of time, and maybe you can like send a question to you, and then you can redirect to someone who can answer it.
Yeah, sure.
Yeah, because like the guy who want to ask is basically the puns in the Pan, Cheng, and Zhang 2021 papers. Yeah. So like below the table that you have, yeah. So like I think he has a specific kind of questions on all this computational related stuff. Yeah, I will we will send an email to you afterwards, and I think like that's all for today. And thanks again, Alexis, for the very inspiring talk. And like I learned quite a lot from here, especially from the hardware side and all the challenges that you guys faced when designing the circuit. Yeah, thanks. Looking forward to have you in the future, and thanks again for your time.
Thank you. Goodbye. Thank you for having me.
Yeah, see you.